Well, I hope everyone enjoyed their lunch, and I apologize for the entertainment. Thank you, Jim, for putting that together. That was excellent. We have two speakers here this afternoon that are going to educate us. The first is Mr. James Crocker. He is the Vice President and General Manager of the Sensing and Exploration Systems at Lockheed Martin Space Systems Company. In his past career, he's been a Program Director for the my notes here. Next Generation Space Telescope at Ball Aerospace and Technologies Corporation. He has a lot of experience with NASA, though, even going back to his days at University of Alabama, Huntsville, where he did some design work for Skylab. He's won numerous awards, including the Space Telescope Science Institute Outstanding Achievement Award and 2 NASA Public Service Awards. So please join me in welcoming James Crocker.
Teflon and Tang. 2 of the famous spin-offs of NASA space exploration not. We all know that there are an enormous number of spin-offs of space exploration, but Tang and Teflon, I'm sure you know, we're not one of them, or 2 of them. A lot of myth goes into what we do in space exploration, and a lot of myth goes into things, and sometimes the things that are true get lost with, and trivial get lost with the important things. And one of the important things, I think the most important contribution that NASA has made was in the area of systems engineering. NASA didn't invent systems engineering, but certainly in the time that we ran up to going to the moon, and since then, NASA has developed this to a state of the art far beyond what industry had before then. And when you think about it, it was the perfect opportunity. Think about the first thing we do in systems engineering is we really set the high-level requirements. And who set those for going to the moon? Well, it certainly came, I don't know who actually wrote the speech for Mr. Kennedy, President Kennedy, but when he said to put a human on the moon before the decade's out and return him safely to the Earth, I think you see the perfect systems engineering high-level requirements. We're going to do it in a time frame that's defined. What are we going to do? We're going to put a human land a human on the moon, and most importantly, at least for that human and his family, bring them back safely to Earth. Systems requirements at that level were part of what laid out the opportunity for us to, in fact, get to the moon before the end of the decade and return the astronauts home safely. So, can you teach systems engineering? Well, absolutely, you can teach systems engineering. That's what you're doing. But teaching something and have people get something aren't necessarily the same thing. And one of the things I've observed is that systems engineering is special. It's different from many of the disciplines that many of us have. I'm an electrical engineer by my undergraduate degree, and I know about electrical engineering. Many of you are probably mechanical engineers or software engineers. And it takes a certain mindset to do engineering. Typically, most of us who go into engineering go very deep into a field. We really know electrical engineering or some subset today, communications engineering or whatever. But to do systems engineering really takes a person who can not only go deep, but who can go very broad. I mean, you've heard of a mile deep and an inch wide. Systems engineers have to be a mile deep and 10 miles wide. I know you know that. But more than that, systems engineers have to do something else. Systems engineers have to be leaders and communicators. And that's not something, I think, that comes natural to many engineers. And so we either have to learn those skills, or we have to have at least a natural ability to carry some of those things out. So why is that important? Well, I think it's important because of a story that's at least 800 years old. And that 800-year-old story, I first heard this story in a book called The Mythical Man Month. It was written about the IBM 360 computer and the operating system that was written for that. At the time, the largest piece of software ever developed for anything. And in that story is a story of some stonecutters and a traveler who, 800 years ago, as the story goes, came up to Avignon, France, on a misty day, and was rushing to a meeting, but he was interested in 3 stonecutters who were working in front of this project. And he asked the first one what he was doing, and the guy sort of grumbled and said, I'm cutting stone. Get away, don't bother cutting stone. So he went up to the second stonemason. He said, so could you tell me, sir, what you're doing? He said, I'm being the best stonemason in the county. And if I work really hard, I can be the best stonemaker in the entire country. He went up to a third stonemason who was just as intent on the carving and the work that he was doing. And he asked him what he was doing. And this stonemason stopped, put down his hammer and chisel, and stepped back, and with maybe a tear but great pride, he looked up and he said, I'm building a cathedral that will stand to the glory of God for the next several centuries. You see, that's what systems engineers do. Systems engineers build cathedrals. When you look back over history and you look at the great things that have been accomplished, things that come to mind like the pyramids, things that come to mind like going to the moon, the International Space Station, you look at the great achievements, the Hubble Space Telescope, and the people who built that were building cathedrals. They may have been, in the case of NASA, cathedrals of the sky, but cathedrals no less. And the essence I've learned over the years of doing that, of building that cathedral, lays at the heart of systems engineering. Today I'm going to talk about a couple of stories, and it's been my experience that you can teach the tools of systems engineering, and that's a necessary part of the foundation. But to actually do systems engineering, you got to go do it. It's not something that you can simulate. It's something that you learn by doing. The basic foundational principles of systems engineering can be learned by all of us, by anyone. Actually conducting systems engineering, the art of systems engineering, the art and science of systems engineering come by doing. I say this all the time. In my career, I've seen over and over and over the confusion of doing systems engineering with using the tools of systems engineering. It takes both, but you can't confuse one with the other, as many of you know. So communication and leadership skills are important. That basic engineering understanding, a broad understanding of engineering and the disciplines that are involved are important. There's a couple of other things that are important too. When I was studying management, program management at school, I noticed that they always form a project office with a program manager, a scheduler, a finance and business operation person, and a systems engineer. That's kind of, you can be a little larger or smaller, you might throw a contracts person in there too, but that's the essence of the program office, right? But of all of those, there's this symbiotic relationship between the systems engineer and the program manager that I found to be extraordinarily deep and extraordinarily important when you're trying to get a cathedral built. And that is this demarcation and this push-pull between the program manager and the systems engineer in a project that, if done right, will lead you to success, and if done wrong, will lead you down some very interesting roads and highways. In my experience, the purpose of the program manager is very similar to the purpose of the systems engineer, but they're a bit of an antithesis with each other. The program manager is to get the program done on time and on schedule. That's their fundamental job. The systems engineer is to make sure that all of those things are done, but also that this thing works. And there's a great book called Launch Systems Failures. It details every failure of every launch and satellite system going back to Sputnik. And in that, as I read it, the thing that struck my mind about this book is that with rare exception, a failure of a system is a failure in systems engineering. It's either a failure of analysis, it's a failure of requirements understanding. I mean, you can go through and just tick it off. This system failed because somebody did not understand the requirement, or it didn't get flowed down properly. This system failed because we didn't test as we fly or fly like we test. Some requirement wasn't understood. So this is about communication, and it's about leadership and understanding that dynamic, and not having either the systems engineer overpower the program manager or the program manager overpower the systems engineer is, I think, critical to what is so important today, which is delivering what was asked for that works on time and on schedule. If either of the systems engineer or the program manager overpowers the other, you'll come in on the wrong side of that equation. You may get something that's phenomenal, eye-watering technically. It may do a million things extremely well. It may have a huge amount of margin. It just may take forever and cost an infinite amount of money. And today, of course we never have, but today particularly we don't have an infinite amount of time and money. On the other hand, if the program manager side of the brain gets too much engaged, you can deliver on cost and on schedule, and you can have system failures. A lot of people talk about faster, better, cheaper, and that it was a failure. No, it wasn't. If you look, in fact, at what Dan Golden said, he said, you know, we're going to do more projects, we will have more failures, but at the end of the day, we will have achieved more. If you look at the statistics on that were exactly what Dan Golden said they would be. He said, you know, we're going to probably lose 3 of 10, but we'll do 10 rather than 5. So that led to, but in that mentality, program managers drove costs down. There was no place where you could say good enough on cost. It was, you know, cheaper, 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 cheaper. And we got to a point where we pushed ourselves off a cliff, perhaps. But still, we did 7 out of 10. So you got to understand that dichotomy and that brain between the program manager and the systems engineer, and getting that balance right, in my experience, is the single most important thing that systems engineers do for the success of the program. So I'm going to stop the theory and go to a couple of, let me get if this one's sorry. So, I'm going to tell you 2 stories, because I think that stories about systems engineering are the best way to learn about systems engineering. I'm going to tell you 2 of my stories, 2 of my experiences, and then we'll talk about them, see what you think, maybe how things could have worked out differently. The first story I'm going to tell you about is this one. Some of you were here and some of you weren't here in the day that we got the first images back from the Hubble Space Telescope. I was up at Johns Hopkins at the Space Telescope Science Institute, and the images came back down, and they were supposed to look like the ones on this side, on my side, and the images looked like images on the left side. The Marshall team was down. They were thinking, well, we're just not focused. If we can, you know, it must be some alignment problem. Worked and worked and worked. And the more people worked, the more they realized there was something fundamentally wrong. I was down in the basement of the Science Institute sitting with Dr. Chris Burrows. Chris is an interesting guy. Chris was at ESA. There's about 15% ESA membership up at the Space Telescope Science Institute at that time. And Chris was an engineer, but I was an astronomer and astrophysicist actually. But Ricardo, the director, said, you need to learn some technical things. So he gave him Born and Wolf, and Chris went back and read it on optics over the weekend. He came back and Ricardo said, you finished it already? And he said, yeah. And he said, so what do you think? He said, well, on page 247, the guy's really wrong. He derived this incorrectly. So you can understand, Chris really knew stuff. He was, I think, the youngest PhD at Cambridge since Isaac Newton. So Chris had written this program, and I said, so what are you looking at? He said, well, I've just analyzed some things, and there's a fundamental flaw in the mirror. Basically, the mirror, I think, has spherical aberration in it. Well, this is the first I've heard about spherical aberration in the telescope, and it was So I said, so what do you do about it? Chris said, well, there's nothing you can do about it. It's built into the mirror, and you can't adjust it out. Those were dark days for a lot of us. It resonated with the country. The Hubble Space Telescope had been, I don't want to say hyped, but certainly anticipated. The day before launch, Brian Gummel had been down. They did a special broadcast. Everybody was looking forward to Hubble. You know, people in the general public like astronomy and telescopes. They can understand it. They can see the pictures. And so this was going to be discovering the secrets of the universe. And so when it became apparent that there was a fundamental flaw in the system, this was the type of press that NASA was getting. And it was not fun to be part of the Hubble Space Telescope program at that time for any of us in academia, where I was at the time, or industry, or in the government, certainly. You remember, this was coming on the heels. This was the second return to flight after the first shuttle accident. People were thinking, NASA's lost their way. They just can't do the big thing anymore. And I would say systems engineering would be at the heart of that. So being a systems engineer, that kind of struck really close to me. So what do you do about that? Well, interestingly, Dr. Holland Ford at Hopkins and Dr. Bob Brown said, well, you know, there's a lot of us who spent our life working on the Hubble Space Telescope. We should put a team of people together, industry, NASA, academia, and let's go broad. I mean, ESA's 15% of this. Let's go get Europeans. Let's get the best engineers, opticians, everybody in the world, and let's go systems engineer this thing. Let's figure out how to fix it. We're not going to, or as Gene Kranz would say, failure here is not an option. We've all invested too much of our lives and careers in this mission to possibly not do everything we can to see how to fix it. Well, in fact, there was a path already going down. JPL was building the Wide Field Planetary Camera 2, which was a replacement for the one on board. And it was serendipitously fairly straightforward to make a correction in the Wide Field Planetary 2 instrument to cancel out the error that was made in the mirror. The mirror was, in essence, as I'm sure all of you know, was ground incorrectly because the tool used to make the telescope was make the mirror had been set up incorrectly. So you can take a 6-inch ruler that's incorrect, and you can cut a 6-inch board all day long, and you will cut it wrong. And that's exactly what they did. They cut, check, but they were using the wrong tool to do it. So Charlie Pellerin thought this was a really good idea. Charlie ran was the associate administrator for space science at the time. And Charlie supported this, he funded this, and we had several meetings to go out and figure it out. Now, it was a pretty interesting approach. This document, actually I Googled it, you can get it online now, talks about the process, the systems engineering process, and the creative process that was put together. And I think what we finally got to a solution, and it was a bigger solution than just replace the wide field. You see, astronomers were on this committee as well. And what the astronomers knew was you can't do astronomy and astrophysics with just an imager. You have to have a spectrograph. The science comes as much or more from the spectrographs than from the imager. So had we rushed up and just put the Wide Field Planetary 2 replacement in on the first servicing mission, changed those two instruments out, we would have maybe had a PR success, but we would not have had a scientific success. So how do you fix all the instruments was the problem. The first thing that we did was all of the team really focused on the optical solution. It was an optical problem, so we got locked onto the optical solution. Peter Drucker, who's a great management guru, said it's more important to be doing the right thing than to be doing things right. Now, at the end of the day, you have to do both. We weren't doing the right thing. You would think, from a systems engineering perspective, that, well, you focus on the optical solution. When I walked in the room the first day, I looked around, and I knew some of the people in the room were eminent optical engineers from Europe, from the U.S., people from JPL, and I thought, man, you know, I'm an electrical engineer, I know a little bit about optics, but I'm not going to be able to work on that problem, so I'm going to think about a different problem that maybe I can work on. But they did a phenomenal job. They basically did all the math. They said, you know, there's 3 places we can fix this. We can fix it in the far field by putting some sort of corrector plate in front of the telescope. We can correct it in the near field, do something between the primary and the secondary. You can do 3 plates. Here's this elegant 3-plate solution that'll allow you to correct the aberration. We can do it in the instrument field, either like the wide field planetary camera 2, where we correct something in the instrument, or we can actually do something in front of the instrument. And in fact, it was Dr. Bodema at Ball Aerospace who had this rather interesting design for a 2-mirror corrector system. But the problem was, we also had an astronaut, Bruce McCandless, who was on this committee. And as we put these ideas forth and ran the math and showed the sensitivity to thermal and vibration of all these different designs and got the best one for this, they turned to Bruce and say, so Bruce, how would we put this in the telescope? McCandless, as you probably know, was on the first deployment mission, but Bruce had worked on making sure the telescope was serviceable and how to do things for really 10 years before more than that, before the telescope was launched. So Bruce knew the Hubble Space Telescope intimately, and Bruce would say, as any astronaut would say, well, I can do that, but they won't let me. They won't let me because it's too fragile to carry up in the shuttle, or they won't let me because it'll place the crew at risk, or you know, you're going to ask me to go down the barrel of this telescope, and you know, they're going to be worried that I'm going to snag my suit or can't get out, so you can't do it. So the very first time Bruce said that, I said, I know what I'm going to work on. I'm going to think about not the fix, or which of the fixes that have been proposed, which are about 30 or 40, all of which would work theoretically. I'm going to think about how would you do the fix, and I'm going to do my trades based on which one of these are easier or actually possible to do. So as I went down that route, there was another problem. So we had all these trades. We'd done all the trades on what was the best optical solution. I started doing trades on, okay, which ones were implementable, and the problem was none of them. Not a single one of the ideas that had been put forth were doable. The corrector plate, which everybody loved on the front, I mean, it was just, I don't know, 3 meter in diameter, 1/4 inch thick magnesium fluoride. I mean, how hard could that be to build and then carry up on a shuttle without breaking it and figuring out how to put it in place? So each one of these I went through. I had built models of the focal plane out of styrofoam. I'm a really great model guy. When I think about things, I like to see them. Built things, and so I was going on and couldn't figure out how to do it. Had an epiphany in a shower in Munich where we were having the last meeting, where the maid had actually left you know, these showers in Europe, they go up and down, and they on the little rods and slide up and down. You see them here now, but in today it was kind of unique. And so I did this and slipped it out, and when I did, it just dawned on me that I had to get into a different thinking space to solve this problem. And the different thinking space was, what if we sacrifice one of the instruments? Because there are 4 instruments in the aft shroud of Hubble. If we sacrificed the least usable, the one most effective, which would be the high-speed photometer, we could put a new instrument in, and all those optics could be in that instrument, and then just like that shower, they could deploy out and put the corrective optics in front of the other instruments. So this is what, because I built these models, I knew that the focal plane of the telescope, where these 4 telephone booth-sized instruments came together, was really only about the size of a large pizza. And all of the apertures for each one of the instruments were fairly close together, I mean, within an area about this big. So if we took one of the instruments out, packaged these optics in it, put the instrument back in, it could then flip out these corrective optics in front of the other instruments. And when I put the chart up, McCandless' face got really, he said, that'll work. He said, that'll work because that's the way we designed the system to be serviced. So what we had done was we had all been focused on the optical solution, which wasn't the problem. The problem was different. The problem was, how do you get the correction into the telescope? And that came up with the idea of COSTAR. And as a matter of fact, if you walk down the block just a few blocks and go to the Smithsonian, this is a picture of COSTAR now deployed over in the Smithsonian. Because on the last servicing mission, when we took the last instrument out, all of the new instruments had this COSTAR correction built into them. So we don't need COSTAR anymore.
Taking it someplace, I'm not sure where.
Taking it someplace.
Yeah, I was just down there the week before last.
Oh, they're going to move it over to where the telescope
So
is.
they've got it packed up.
So they got it packed up. Okay, so you can't look at it. So that was kind of one thing. So the first lesson I got from this is make sure you're solving the right problem. It's so easy to get locked into solving a problem that you know how to. It's sort of like, you know, when you lose your contacts or you lose something and it's dark, you want to go look for it by a street light. It's really easy to get locked into doing something that you know how to do, as opposed to solving the real systems engineering problem in trade of understanding what the real problem is. And so that was the lesson to me from COSTAR. The other thing is one about leadership and salesmanship. When we proposed this idea, we all thought, I mean, it was so hard to get here. We thought it was just the obvious solution. When we tried to sell that, we got a million reasons why you shouldn't. And the one that was the most powerful, the one I had to think about the most was, well, wait a minute. If you put this in the telescope and you deploy all these arms, and you can't get it out of the telescope on the next servicing mission, we've not only lost, or it doesn't work, we've not only lost this instrument, we've lost all the axial instruments. So we thought about all of the secondary implications, the unintended consequences of putting COSTAR in. And we had a simple solution, and that was by some simple design features, we eliminated that problem. Number one, each of these arms naturally would have a dual redundant motor to deploy it or stow it. But if both of those fail, there's a little shoe here, and when you retract the tower, those little shoes flip each one of the mirrors up. And then somebody we knew would say, well, so what if you can't retract the tower? We said, we'll have a dual winding on the motor, but on top of that, there's this 7/16 inch bolt. That's what the astronauts use to actually install all of these instruments. You run that bolt back, it turns the whole motor arm, not the motor itself, but the whole casing. So even if the bearings are frozen up, it would pull this back. So we had anticipated what the objections would be, and we had simple, I mean, this didn't add anything to the design on the front end. Putting a shoe on this on the front end costs nothing. Putting a 7/16 inch retraction that'll pull the whole thing back when you're doing the design really was a design issue. It cost nothing. So it added nothing. Now, to do it on the other end would have been enormously expensive, so we had thought about that. So, as I think all of you know, the wide field planetary camera was successfully installed along with COSTAR on the first servicing mission. I think we did this in 30 some odd months from the time we started till the time we got it done. But to me, it was the two big lessons that I learned personally out of this were, number one, it's more important to be doing the right thing than to be doing things right. At the end of the day, you have to do both. But if you're not working on the right problem, you will never get to the right solution. And then secondly, part of systems engineering, particularly a new approach to doing something, you really have to think through this whole thing to the end. What are the objections going to be? Not only from a technical, but from risk, particularly from risk, and this also the political environment that you're working in. NASA at the time could not afford a failure. We could not go up and service the Hubble Space Telescope and fail. I mean, quite literally, we were betting the agency that this would be successful. Three strikes and you're out. I mean, if we were not successful, or even the perception of not being successful, it could have been a very bad day. So that's CoStar, and of course, it was installed on the first servicing mission. KT was able to use the standard procedures to go in. She pulled the old high-speed photometer out, installed CoStar, deployed it, everything came up, and it worked because this was the way it was designed to be serviced. So we took advantage of a built-in design feature. And then on the last servicing mission that we just completed, CoStar was removed and the cosmic ordnance spectrograph installed in its place. And now, for the first time, we have the real power of Hubble. All 5 of the science instruments are working on Hubble and returning phenomenal results. Let me tell you about one other interesting story, and it's about, I'll be brief on this. I want to talk just a little bit about the James Webb Space Telescope. I could spend a lot of time talking about Webb, but let me just tell you one story. The challenge with Webb, challenge with the James Webb Space Telescope, fundamentally was how do you package a cryogenic, at the time, 8-meter telescope for launch in such a way that you can reliably deploy it at the end of the day. And there were several designs. I won't go into all of them, but there were 3 kind of fundamental designs at the end of the day. One was called the hard, which was hexagons that kind of, unfolded. One would flip over, another would flip over, and you stack them like potato chips. The interesting thing about that approach was that was the most volume efficient way to package an optic. Basically, stack them like potato chips and then pour it in and fold. There was another one that was interesting, and basically, mirrors are mirrors. Another that was interesting was basically one that was kind of popular design. It had never been flown, but people basically took the mirror and they broke it into a fold-up, fold-down pedal. So that was the fold-up, fold-down pedal approach. That's pretty good. I mean, basically, you get up there, the secondary mirror is fixed on a tower, and basically you fold these 2 up and these 2 back, and you got a mirror. And that was kind of the preferred thinking of the design. There's 2 problems with that. I mean, one is you've got, actually it was 3 pedals up, 3 down, so you got 6 deployments. And if any one of them fails, you have a problem. With the hard approach, the hexagon approach, I think there were 38 deployments that you had to do. So I'm using this paper plate because the late Wally Meyer from Ball and Bob Woodruff, who was a fabulous optical designer, and myself were sitting in the back of the room up at Goddard when they were having the industry day, and we're thinking about this. And we were thinking, okay, we know a lot about the requirements for this telescope. We have to quit thinking about what's the way you fold it and think about, what's the right way to be thinking about this problem. And it's really twofold. The 2 biggest problems you have to solve were, number 1, how do you fold it so that you can deploy it the most reliably with the fewest number of deployments, number 1. And number 2, this is a cryogenic telescope. It operates at, in the several, a few tens of Kelvin degrees. And so the other problem is going to be the thermal connectivity of the backplane. You get a degree or 2 difference across the backplane because of its conductivity, and it's not going to hold its shape. So there were some pipe plates. You know how hard it is to find these today? These were in the back of the room at Goddard at the time. So I went up and picked up a pipe plate, and I said, Wally, if we fold it like a table, like one of these drop leaf tables, then, and as a matter of fact, if this is the reflective surface, and then the secondary is on a 3-bar linkage, then to really get a really good 4x8 meter telescope, you just get 1 deployment. Basically, the secondary's got to flip down. And then if the 2 wings do deploy, then you've got a full 8-meter telescope, and you've done it with 3 deployments. And that was like half of anything else. But the most important thing was every other design tore the backplane. And when you tear a backplane, you've got to put the thermal conductivity back together. So you're dependent on some sort of connection now that you got to remake for the thermal conductivity. Whereas if you fold it, you don't have to tear the backplane. And you could even imagine having a copper strip down the fold here so that you have a continuous thermal backplane across it. So in essence, although Ball teamed with TRW and this sort of thing, that concept of the design actually survived. And so when you look at the James Webb Space Telescope today, you'll see this chord fold, we call it, or drop leaf table fold. And the way we got to that design was thinking about what the real problem was. Here again, if you're designing a telescope, you get locked into the optical design, and you miss the fact that for this application, the optical design was interesting, but how to fold it and package it for maximum reliability on deployment, and at the same time, how to get that thermal conductivity of the backplane were the two deep systems engineering requirements. So the thing I learned here again from this is, it's more important to be doing the right thing before you do things right. And so both of those were really great education for me. So you can see how the telescope is stowed, and basically the 3-bar linkage deploys the secondary. Once that happens, you've got a really good telescope at that point. And at that point, you've got a telescope that actually performed about 80% of spec. And then you deploy the two outlying wings, and you got the whole thing. So systems engineering is an art, and I say it's an art because it's art in the sense of practice. You don't learn to play an instrument by reading books. You learn to play an instrument by playing an instrument. And if you're going to play in an orchestra, you learn to play an instrument by playing with others. And the thing that I like most about these stories is that you're playing with others. It was not, when you look at both of these in retrospect from this side, well, of course, that's the way you would do it. But when you look at them from the other side, when you don't know how to go install this thing, it's different. It's the best solutions are, well, of course you would do it that way when you figure it out. But trying to figure it out is not easy. So getting your mind into a systems engineering approach of what's the right question to do this. I think if you just take one thing away from what I've told you today, it's more important, or first, I would say, make sure you're doing the right thing, because you can't do the wrong thing right, no matter how hard you try. So with that, I'd like to spend a few minutes with questions. I'm glad to take, we play Stump the Speaker. Is there a mic? Do you need a microphone?
Jim, I'm going to make an observation though, is
Okay.
that no matter how
obvious that thing looks now, and you made pretty light of how hard that thing was to build.
Yeah.
That over and above the fundamental systems design, there was a lot of work that went into trying to figure out just how to make that thing work, or whether there wasn't a better way.
So I'll tell you just 2 quick stories on that. The other thing you had to know about CoStar was you had to have a really deep understanding of what was possible. The optics on this telescope were state-of-the-art. They were as good as engineers could achieve, laws of physics would allow. I'll just tell you a little story about these optics, which are the size of nickel, dimes, and quarters. Well, the guys assured me that the optics were doable. So, of course, when you come up with an idea, I got asked to be the team leader to go build this thing. So we put out a contract to HDOS, Kodak, HDOS, and UTOS to build these optics. We were going to let, there were 3 sets. We were going to let each team start with a different set, and whoever got them first, we would take them. We had to have these optics. Well, they started making these optics, and they couldn't make them. Well, why not? So I fly out there, and I start listening to the presentation, and the guy said, well, it's because they're anamorphic A-spheres on a toroidal blank. I said, okay, so tell me what that means. Oh, they're potato chips. Like, oh, okay, so we got to make an optic that's like got a different radius of curvature in this direction and in this direction, and we have to polish them to 3 angstroms RMS surface roughness. I mean, that's like, 3 atoms out of place. And so they couldn't do it. Well, Frank comes up to me and says, well, there's this little company out in California named Tinsley, and I think they can make these optics. So we get on a plane, we fly out there, and they said, yeah, we can make those. And I said, well, show us how. I said, we can't. I mean, you can't. Well, we do it in this back room. So we thought, man, this is going to be expensive because we got these other 3 contracts. So we said, well, give us a price. Well, they came back and said, well, we'll make them all for, I don't know, $250,000. It's like, wait a minute, that's less. These guys can't know what they're doing. It's less than what any one of the other vendors was charging us for 1 optic. Anyway, long story short, they went in the back of the room, they came out, they made all the optics, they did it in time. All the other 3 vendors failed. That's how close we were. If we hadn't have found Tinsley, we wouldn't have been successful. The second thing that made this hard was you had to know where the entrance apertures to the other instruments were, to 0.1 millimeters. And we're thinking, we're not going to be able to get that accurate enough for drawings. Until I ran into the cafeteria to Olivia Lupin. Olivia was with the high-speed photometer team, the instrument that we were taking out and sacrificing. They were pretty upset with us that we were taking their instrument out and sacrificing it to put this in. So I was talking to Olivia, and I don't know how this problem came up. She said, oh, that's not hard. I said, what do you mean it's not hard? She said, ooh, ooh, ooh. She gets really excited. She said, that's what I've been doing for the last 10 years. What? Well, the PI, Bob Bless, hired me because I have to know where every one of those apertures are, because the high-speed photometer, basically, you're going to be looking at a star with another instrument, and then I wrote the software to send a command to not only move that star into the high-speed photometer aperture, but to a particular filter in there. She said, I know all of this to 1/10 of a millimeter. So I said, oh, you're on our team, Olivia. So Olivia came in there. So a lot of this was communication. If we'd have tried to do this on our own, we would have failed. Seppi at Goddard knew these instrument vendors, had been building all of these instruments. Olivia had been working for decades to get all this. So how to deploy it, how to get that right, how to get the optics right, how to hold this thermally. So it was a real study in communication and reaching out to the industry. But the thing we had was everybody working on that program then and today were building a cathedral, and everybody really got together to make it work. But this was really hard. It was really hard. We were very fortunate that we were able to pull this together. It really took a team of incredible number of people to make this work.
Question, and it'll probably be real hard to answer, but oftentimes, even throughout history, not just what we're doing in NASA, serendipity occurs. Stuff happens, and fixes arise. You mentioned communication. What are some other things that would kind of help foment serendipity? Because it seems like a lot of success comes out of that.
I couldn't agree with you more about the serendipity part. I'll say 2 things about it. One is there's a wonderful series. There's actually a book. It was also an NPR series called Connections by Burke. And he talked about how coal miners in Wales ended up needing a pump, and because of that, it really led to the development of the internal combustion engine. So you go on, there's these serendipitous things. My experience is, as a matter of fact, there's a recent book out that actually says the rise of humans as a species actually came about because of trade, because cities actually formed as trading centers and ideas spread like viruses. So somebody who was building boats would learn about something that somebody was doing, building carts, and so it was this serendipity actually led to an explosion and to why humans dominate the planet. I don't know if I believe that or not, but that's some of the latest theories in anthropology. So I think that to help that process, two things have to happen. One, systems engineers, who are usually the architects of these systems, need to be more than broad across their discipline. They need to be broad. And by that, I mean, if you look in my briefcase, I'm reading The Power Broker, which is about politics in New York in the 30s. And I tell you, if you don't think that what we do has some political side to it, you should think again. And another book is The Cambridge Lectures by Hawking. And so I think that, first of all, you got to get out and read what's going on or has gone on across a number of fields. When you look at new ways of doing things that come into a field, they usually come from another field. So you just need to be broad in your reading. But secondly, it's this kind of interaction. It's getting people together and telling their stories about what worked, what doesn't work, this sort of thing. And it's like I'm so pleased to see having somebody from GM come in and speak, because I mean the automobile industry is going through a revolution in innovation right now as they switch to electric vehicles, and the thinking of how to put all of that together. It's a really hard question, but I think that we're driven because of being engineers to go deep into something. We have to want to get out and go broad. And in fact, the best systems engineers, I personally think, are those that just have an immense amount of curiosity. When you go up to something and you see something that has nothing to do with anything you're doing on a day-to-day basis, and you don't understand it, or you don't understand why somebody does it that way, you just have this burning desire to say, gee, I wonder why they did it that way. And so I think it's that desire that sets the best systems engineers apart, that they really don't like anything they don't understand, why somebody did something that way. There's almost always a reason for the irrationality of humans, and it's usually not irrational when you get to the bottom. It's just getting to the bottom is really hard.
I just have a comment. I'm working on a JWST, and I'm the lead mechanism engineer for Optical Telescope. And I know that's it's a nightmare for mechanism engineers.
That's why you want the fewest number possible.
Yes, and because each, there are 18 segments, and each has 7 actuators. And not only that, but that portion works on a cryo, but the electronics is on the warm side, underneath the sunshade.
Hardest telescope ever been designed.
Yes. So, I like to have a success, because I don't want my name to be on the Washington Post, okay? But it's a really, I think it's we are cutting into the edge of technology to drive not only the actuators, but how we can do the radiation-wise, thermal-wise, and electrical-wise, that we can drive this mechanism as well as the optics to get a better picture than Hubble.
Yeah, James Webb is an incredible machine, and at the end of the day, cryo actuators of the kind of precision that you need are incredibly challenging, never been done before. So that's why, knowing that, having built cryo instruments previously, I knew that the minimum number of actuators would be a good thing.
So right now it's almost 138 plus.
And most of those are on the primary segments. There's another story talking about connectivity. Do you know where the primary segments came from for Webb? So I was sitting down. I got asked to go over by Riccardo Giacconi, who was head of Space Telescope Science Institute, who was Italian. He got asked to go over to Europe because they had a program over there called the VLT. That was $1 billion over budget and slipping year for year. So Riccardo called me up, and I went over there. Long story short, one of the major problems with the VLT was the secondary mirror. The secondary mirror had to chop at like 30 hertz. And basically, this 8-meter telescope, and the secondary mirror is like 1 meter one, and weighs a lot, and so when you chop at 20 hertz, it shakes the whole telescope. So we had to do something lighter. They were trying to do it out of silicon carbide, but we couldn't make silicon carbide, and they cracked. I said, well, let's do it on beryllium. And everybody looked at me like I was an idiot. And I said, well, no, beryllium would be great, because it has the lowest Young's modulus, it has the best Young's modulus, and you can machine it and lightweight it. So we made these 1.1 meter beryllium secondaries for the VOT. We made them on time, on schedule. We put them on the telescope. They chop them. They're lightweight. They're stiff. They don't move. And so when we were sitting in the back room, Wally said, so what kind of, everybody's using zero doers. I said, let's not use zero doers. That'd be the wrong thing. Let's use beryllium. I said, gee, that'd be really hard. He said, no, it's not hard. You go to Brush-Wellman. See, so we had developed the supply chain. So you go to Brush-Wellman. They got this spherical hip powder. You can hip it, then you can machine it. And the guys to machine it are down at Axis. It used to be Speed Reading down in Coleman, Alabama. And they just made these mirrors for the VLT telescope, and they're all set up to go. And then we'll take it out to Tinsley, because Tinsley can actually polish these beryllium. Because when we were out there building the Hubble telescope mirrors, I happened to look in there, and they were building all this beryllium stuff for another customer, who will remain nameless. And so I know they can do that. So here again, it was that serendipity connectivity, because if you tried to go sell a beryllium telescope and you couldn't point to the fact that there's already, the TRL level would have been considered, insane, because we had serendipitously, we had developed these beryllium mirrors for another telescope. So, but here you go. So serendipity.
Question here. I guess my question is geared more toward trying to dig out some insights about collaboration versus intellectual property protection. And we're moving into a new era where we're trying to spur the growth of the commercial sector, particularly for space launch. So as we're starting to think about those things, I know that various companies out there would love to see intellectual property protection on our part so that there could be a competitive advantage for them. That apparently rolls back to what we do on a day-to-day basis. And yet and still, as systems engineers, we really want to talk about these things because it's the sparks we get from others. Could you share some insights of maybe your spin on where you think NASA could or should be?
So the question is intellectual property, and it's a great question. We can start by recommending a book to you. And the book is called The Birth of Plenty. And it asks the fundamental question, what happened in the late 1700s that caused an acceleration in people's lifestyle worldwide? What happened? What were the things that came together? Because for millions of years before that, fundamentally people lived at, 99% of people lived, 99.9% of people lived at a subsistence level. So the book explores the things that came together that changed, revolutionized things. And I won't list them all, I'll just tell you one. One was property rights. And basically, if I can have a way where I'm legally protected so that the fruits of my invention are protected, it encourages me to go off and do something. Many systems and countries before that time, as a matter of fact, my grandfather, my great-grandfather, claims to have invented, and I don't know this, but he claims to have invented the Coleman planter, which is a seed planter that kind of revolutionized planting and pulled behind, and it was stolen from him. Okay? So that was kind of the way that things worked. The law did not protect property rights, either land or particularly ideas. The first telescope actually was patented in 1608 by Hans Lippershey in the Netherlands. He didn't get the patent because they said, oh, gee, just putting two pieces. How could that be? You didn't invent anything. You just put two pieces of glass together. Truth of the matter is, they saw the military application and they were hoping to keep it quiet because you can spy scope, right? So this whole thing about property rights really comes down to a deeper level of you want to share things, right? But when you don't have the ability for companies to have property rights, then you won't get investment from companies. So a company's not going to put $100 million into something unless they can protect that investment or those ideas in one of two ways. One is trade secrets, so they just don't tell you what they're doing. That doesn't work well in our environment because we want to know what you're doing, because we want to know if it's going to work. Because just because you're building a rocket, and you may give me the rocket, I'm going to put $1 billion satellite on it, so I want to know that your rocket is going to be successful. So the way this has kind of worked itself out in our society is in academia, people get rewarded for publishing. So you get tenure because you've shared your ideas, and that's how you get rewarded. In the industrial side, basically, you spend your money, your time, and your investment, and you get intellectual property. And so that's how you get rewarded. I do work, I read with a number of universities, and the biggest problem we have with universities is getting the property rights to the IRAD worked out. Some universities want you to give them money and do the research, and then they'll publish it. But it's hard to convince a stockholder that you should give me money so I can give it to somebody else so they can share it with everybody. So this is a really hard problem. So, however, what I believe is that the way you approach this is in two levels. One is basic research. You really don't know what the application is. You're doing basic research maybe to get some ahas, and usually when you get basic research, that's 10% of the problem, getting it to a commercializable, usable form where all the money gets invested. So a lot of times the TRL 01 things, people kind of share that because it leads to these serendipitous things and that sort of thing. But above that, it's very hard to do. I don't know how you do it because you got to tell me what the incentive is. There's certainly an incentive on the user side to get as much free stuff as you can, but that incentive is a little short-sighted because what you really want to do is have companies invest either their own money or their own IRAD or if nothing else, then their A team to be working on your problem. But if they don't walk away with something from that, they have a hard time explaining it to the people who pay their salaries or to the shareholders who support it. It's a really interesting problem, and the only way I've seen it really work in the long term is at the end of the day, somebody has to walk out with something that has either a trade secret or an IP, intellectual property to it. Otherwise, it's like the Coleman Planner. If you think you're going to invest all of your time and effort into this, and then you will have no fruits of your labor at the other side, it will stifle creativity and innovation. At least that's what the Birth of Plenty says.